Well, I'd like to welcome, and excuse me if I'm mispronouncing your name, Slava Turyshev
Perfect. Mark, you got it.
and Lou Friedman, who are here to talk about something that's really novel, and that is imaging, getting high resolution imaging of exoplanets by going way far away and using the sun as a gravitational lens. And fantastic work. And so I'll turn it over to you, Slava.
Mark, thank you very much for the introduction and for the opportunity to talk to a broader audience with the Planetary Science Institute. This is an incredible opportunity for us because for the last 4 to 5 years, we were focusing on optical properties of the solar gravitational lens. And the key here is to use solar gravity as a lens. Essentially, we studied optical properties and we were able to confirm that indeed this science fiction idea that used to be discussed in the past is actually has a very significant opportunities, very significant capabilities for imaging. So imaging and mission design were two our primary efforts for the last 4 to 5 years. Now, once we realize that this lens has a very unique capability for imaging, we are turning the page and we invite broader community to study its use and essentially biosignatures and studying those planets in the sense of planetary sciences. Because, you know, when astrophysicists discover exoplanets using direct imaging technique, we don't really have the capability now to study those objects. We have the capability to discover them, but with the solar gravity lens, we actually can explore them in the sense of planetary sciences. Like you fly a spacecraft to Saturn, and then we study every satellite that orbits Saturn. If you fly to Jupiter, it's a planetary science mission. We study pretty much every satellite of Jupiter. In the same sense, we look at this opportunity flying a mission of flying a spacecraft to study exoplanets with the solar gravitational lens, and studying not only one exoplanet that orbits that host star, but really the whole planetary system. And so here I'm pleased to give you a little overview of this effort that we are now developing. And so I would like to invite your participation and thinking, and please do interrupt me as you wish, because interruption helps to create important conversations. So we talk about direct imaging, direct multipixel imaging and spectroscopy of exoplanets using solar gravitational lens. And in the past, you know, like Carl Sagan used to say, every extraordinary claim requires an extraordinary evidence. We had that idea that sun may be used as a magnificent lens, but we didn't know the fully capable, we didn't have the fully capable formalism and understanding of optical properties of that object, the sun. And so now we have that evidence, and I think we are about to begin claiming more that we need to put more efforts in studying solar gravity lens for multiple purposes. Why do we do that? And essentially, let me start. Okay, this is it. So when talking about exoplanets, of course, our challenges is one of our challenges is light amplification. Here you see a selfie that was taken by Cassini spacecraft. A selfie showing Earth, and pretty much it's everybody in this room. It's all us are showing on the planet Earth. So light amplification is significant because those objects that you would like to study are faint, they are far, and to get a significant photon flux requires a significant aperture sizes. So this is another interesting picture. See, it's Curiosity rover on Mars taken, again, we're looking at Earth. And so if you increase a little resolution on the mast camera on Curiosity, you see both Earth and the Moon. So we need not only light amplification, but also resolution, because observing objects such as our Earth is a little rock on this chart, little rock that is much smaller than the sun on the background of the sun. It's very difficult. So we're looking at resolving those objects with multiple pixels. In the past, it's just not really possible, because to do that, you need to have access to very significant optical apertures. For example, those pictures that you see here, those little videos showing our ability to detect exoplanets using direct imaging method. And we are able to do this for super Jupiters that are orbiting their host stars at quite significant distances from them. To use this method to discover exo-Earth would be quite challenging, if even possible. So you see this multiple sort of objects were discovered using direct imaging method, and resolving those objects with the technique that we have now, it's impossible, because the technology that is needed is not available. So realistically, if I'm taking our own planet, our own Earth, with a diameter of 13,000 kilometers, and I put it at about 30 parsec, or let's say 100 light years away, to resolve that object with just 1 pixel, I need to have access to a telescope with the aperture of 90 kilometers. So for those of you who are familiar with Los Angeles, you see Jet Propulsion Laboratory is conveniently placed in the middle of that chart, and Dana Point is way down there. So essentially, it's 90 kilometers aperture, must be in space. And realistically, this is just not happening, because only today we saw a flight, I guess, as New Glenn have flown to just beyond the von Karman line, which is 100 kilometers away. And so that just building a telescope with that aperture size is just not possible. And realistically, we are all used to seeing pictures with multipixels, and this blue marble picture showing our own planet with resolution of 1 kilometer per pixel. Can we have something like that observing exoplanets? Is there a technology that allows us to do that? Let's look at what we have today. Realistically, so this is the telescope. This is the telescopes that we are building today, that we have built in the past. And so this is the history of roughly 150 years of telescope construction. And on the left, this is European extremely large telescope that is being built in Chile. And so the diameter of that telescope is 39 meters. Nowhere kilometers, it's meters. And realistically, even the radio telescopes, we have 500 kilometers, 500 meters, even radio telescopes. But talking about optical instruments, that is not happening. Speaking about space deployment, here you see Kepler, which is 1.4 meters. Of course, Hubble 2.4 meters, and soon we hope James Webb will be in space with its 6.5 meter diameter. So seeing anything on the scale of kilometers, it's not possible. And even putting in the interferometer, let's say you have a 30-meter telescope in space, you have 2 of those telescopes in space separated by a couple astronomical units. And so you can form an interferometer. Even that telescope will require significant integration time. Both of these 30-meter telescopes in space will have to have external coronagraph, and then integrating signal will require pretty much on a scale of shy of a few million years. So it's not happening even on that with this approach. So we need to look at something very drastic and see if there is something that nature helps us with. And this is why we start looking at solar gravitational lensing. So here in this chart, you see our sun, the solar system. On the left, we begin with the sun, then there is a solar system. And somewhere in the middle, if you see my cursor, you see Voyager 2 spacecraft, which is now a distance of roughly 155 astronomical units away. And then because this is logarithmic scale, it goes all the way to Alpha Centauri. And so in the middle, conveniently placed in the middle, the solar gravitational lenses, solar gravitational lensing region. The challenge here, of course, is the distance, because the sun, indeed, according to general relativity, acts as a lens, because when a light travels around a massive body, the trajectory of light ray is bent towards the mass. And here on the bottom of this chart, you see pretty much a scheme how that works. Depending on the impact parameter, you see that the rays that are touching the solar photosphere, they will intersect at the distance of roughly 547 astronomical units away. And the light rays with the larger impact parameters will intersect further. And so this lens does not have a single focal point. It has a semi-focal line, which begins at 547 astronomical units and extends way beyond 2000 astronomical units. Somewhere in the very immediate vicinity of that focal line, there is something that we call strong interference region. Strong interference region, this is where the light rays that pass by the sun with similar impact parameters, they will interfere constructively and providing very significant optical gain. And so for if I take that object Earth, put it 100 light years away, and so the solar gravitational lens will compress that object. The image of that object will be 1.3 meters or kilometers, 1.3 kilometers. And if I fly a spacecraft within this cylinder with a diameter of 1.3 kilometers and look back at the sun, I can see the Einstein ring that is formed around the sun, and that will provide me the data about exoplanets. But before I do that, I need to block the sun. Essentially, when you buy a telescope, everybody tells you, don't look at the sun. But this is exactly what we are going to be doing here, because we need to look back at the sun. We need to block the sun. So we're using a very modest coronagraph. We don't need a coronagraph like W first, 10 to the minus 10. The ratio here that we would like to achieve, and that this is quite comfortable, 10 to the minus 7. And so blocking the sun, so solar light at the level of 10 to the minus 7 is sufficient for us to start seeing Einstein ring formed around the sun. And so here on the bottom chart, you see the Earth-like exoplanet, and it reflects rays of light. And then this light propagates towards the sun. Solar gravity bends it, and then if you fly a spacecraft, let's say 1 meter telescope going in the focal region of the solar gravitational lens, and if that telescope has a coronagraph going in this image, going within the image, the spacecraft will collect data going from pixel to pixel, and at each location the spacecraft will record brightness of the Einstein ring. I will talk about the imaging capability a little bit later, but to get things in perspective, imagine yourself sitting in a movie theater, and in front of you see a white screen. Behind you have a projector. That projector projects a movie on the screen, and because the light is reflected from that white screen, you're getting the images on your retina, on the eyes. And so that's how the sort of movie projection works. But now sun does the same. Sun actually acts as a projector, but there is no screen. There is a cylinder. The image is formed within the cylinder with a diameter of 1.3 kilometers. Putting a spacecraft in that region, in the strong gravitational strong interference region, there is no screen. Spacecraft needs to look back at the sun, and it needs to move from pixel to pixel, sort of recording the brightness of the Einstein ring at the given pixel location. So this is our data, scanning, going pixel to pixel, collecting the brightness of the Einstein ring. This is what spacecraft will have to do. And so that's sort of in a nutshell. But let me go.
Excuse me.
Yes, please.
So at the focal line, the diameter orthogonal to the direction of the sun of the Einstein ring that's imaged there is 1.3 kilometers or whatever.
Correctly. Yeah, okay. This is correct. This is image size.
Yeah, the image size, right.
It's, of course, it will be a sort of target dependent, but if I'm taking our own Earth, 13,000 kilometers, compression will be at roughly 1.3 kilometers image diameter.
And is that independent of the distance of the target?
It is of course dependent on the distance. If I take a closer target, let's say not 100 light years away, but if I take, let's say 10 light years away, so it will increase by tenfold. So it will be not 1.3 kilometers, it will be 13 kilometers in diameter.
Okay, makes Proxima Centauri more tough.
It's about 30 kilometers in diameter, and Proxima Centauri is actually a very easy target for that, because we don't need to sample every pixel. We can skip a few pixels, and we can make a magnificent image of the Proxima Centauri system with this telescope. Because the closer we are, the less stellar spherical aberration that is inherited with sort of which is one of the characteristics of the gravitational lensing. So the spherical aberration will play a lesser role in this case. The image will be magnificent. The closer that the target is, the image will be much better. Okay. So moving on. So the idea of using the sun as a gravitational lens was proposed by von Eshelman. Von Eshelman, he was a professor of physics at Stanford University, and he also was the PI on a radio science experiment on Voyager 1 spacecraft. And back then in '79, he published this paper in Science suggesting that solar gravitational lensing can be used to communicate with alien life. And so that was just a few numbers, interesting idea, but basically the wave optical treatment was not developed. And so the opportunity was there, but was waiting to be computed. We realized in our work that radio waves are not very good with the solar gravitational lens, because the sun actually acts as a negative refraction index. And so it's actually the light that goes around the sun will be defocused by solar plasma, but gravity is focusing it. So plasma and the gravity work in sort of in opposite directions. The radio waves are not really, so the radio waves are longer than 1 centimeter in wavelength. They will not be benefiting from solar gravitational lens, because solar plasma will actually destroy the lensing. But for shorter wavelength, optical, infrared region, this effect is very minimal, and so a solar gravitational lensing is quite good for this for these ranges. So what we do, we look at, let's say, this is a great image taken by Hubble telescope. So this is Einstein ring formed around a galaxy. So then we are looking at Einstein ring 1.3 kilometers. When we block that the solar light with the coronagraph, therefore we see this 1.3 kilometers image thickness of the Einstein ring that provides us the data on the exoplanet. Moving on. Okay, so this is sort of the summary of optical properties of the solar gravitational lensing. On the optical axis, for the wavelength of 1 micron, solar gravitational lens provides an amplification factor of 10 to the 11th, because amplification factor scales with the ratio of Schwarzschild radius divided by the wavelength of that you use for observation. So for optical frequencies, for optical wavelength, we're talking about 10 to the 11th. And so now if we include the fact that the sun is not spherical, but actually it's extended, it has quadrupole, it has octupole. And so the quadrupole actually quite interesting. It forms not a point spread function, doesn't look like the one that we show here. So this is point spread function of a monopole sun, compared to the typical classical telescope, which is scaled with the Bessel 1 square. The solar gravitational lens scales with Bessel 0 square. So essentially this is where it creates a blur with the image. And so blurring of the images is something that can be removed using deconvolution technique, and I will talk about this. So also solar gravitational lens provides us with very high angular resolution of roughly 0.5 nanoseconds, which is not possible to achieve with any other means currently. So that allows us to think about imaging a distant objects such as the Earth at 100 light years away with resolution of roughly 15 or 20 kilometers on the surface of those objects. And so we're talking about continental lines, weather pattern, topography, ice caps, you name it. So it's quite interesting in terms of imaging capabilities. As I said at the beginning, our current challenge is actually to translate that into spectroscopy, because imaging by itself is wonderful, but we need to make sure that we can actually do spectroscopy with the solar gravitational lens. And essentially, looking at oxygen, nitrogen, methane lines within optical domain and near infrared will tell us a lot of useful information about the conditions that are current on that object, and that needs to be studied in the near future, because now we have very good understanding of optical properties of the lens, and we need to understand how we can actually benefit from those going into spectroscopy. And as I mentioned in the past, that the lens forms a very sharp beam, pencil beam, where entire image is compressed to very much smaller cylinder with a diameter of, let's say in this case, 1.3 kilometers. Moving on. On the left, we did a lot of simulations. I will not show all of them, but here on the left, you see a regional image at 1,000 by 1,000 pixels. So now if you convolve that image with the point spread function of the solar gravitational lens, you see the image that is formed on the right. You see it's kind of blurred. And so blurring is because of the spherical aberration that is due to, it's a nature of the gravitational lensing. But even with this blurred image, you can kind of recognize some continental lines, and you can see that, yes, indeed, there is some structure on the surface of that object. But then we have developed very capable deconvolution techniques that actually allow you to recover that, to improve that imaging. So the blurring or deconvolution allows you to actually get quite good quality of image reconstruction. Again, on the left, you see the original image, and on the right, you see different images that were deconvolved from the data. And essentially, you can see that at different resolutions, we can get quite interesting features on the surface of those objects. So that is something that this work is ongoing, and actually results are quite interesting. So, but moving on, I guess I need to, okay. So of course the sun is not naked. There is a solar corona, there is significant brightness. And the challenge here is that we need to be able to work with this, our own sun, to be able to block the sun as much as we can. And so, of course, the sun is not static, it's variable. There is a temporal variation in its intensity, and the solar corona is quite interesting. If you look at this chart, you see that when we have spacecraft placed at 600 astronomical units, Einstein ring will be separated by just about 1.2 solar radii. We cannot observe at 547 astronomical units because Einstein ring is touching the sun, and it will be very difficult to build a coronagraph that will be able to remove the sunlight and actually work with to leave only the Einstein ring. So therefore, we travel a little bit further because of the solar corona. And so the region for our mission is between 600 astronomical units and 900 astronomical units, where we need to be able to design a coronagraph that will block the sun at that level. So, but not only the sun, also we understand that there is solar corona. We can block the sun, but we cannot block, we should not even attempt to block the sun below much higher than the solar corona, because solar corona will still shine through onto the imaging sensor. And so we need to be able to block the sun at the level of solar corona. And so we have studied a significant, we have invested significant efforts to study the design of coronagraph. And essentially we are capable now to have a prototype for the solar coronagraph that actually shows these capabilities. Moving on, that's just a scheme how it works. So again, the blue curve here is the Einstein ring. The dark circle here is the kind of naked sun without solar corona and the solar brightness. But now, of course, the sun is bright and the solar corona is there as well. So what we do, okay, so let me do this. Okay, so this is with the coronagraph, we block the sun with the coronagraph. And then what we do next, so I guess it's not transmitting fast enough, maybe this. So our telescope that is positioned at, let's say, 600 astronomical units, it will look at the sun, it will not, its resolution element will be sort of lambda over d. So this is the size of the resolution element of the telescope that is positioned at focal region. So therefore, as we observe the Einstein ring, and you see this is Einstein ring, so essentially we get all the light that is within the Einstein ring a little bit sort of in and out of the sun because of the resolution element. We cannot resolve the thickness of the Einstein ring, but we resolve circumference of the Einstein ring, because the thickness of the Einstein ring is 1.3 kilometers, but from the distance of, let's say, 600 astronomical units, we cannot resolve the thickness, but we see the circumference of the Einstein ring. So our coronagraph, essentially the annular coronagraph, that actually blocks the sun and gets light from this belt, from this annulus. And so essentially, this is the sort of summary of our simulations for the solar coronagraph. We are able to achieve a very significant contrast ratio of the level of 10 to the minus 7, 10 to the minus 8, which enables us to discuss the imaging with the solar gravitational lens using a very capable coronagraph. So the coronagraph is not an issue. The work is being designed, is progressing, and at some point we'll have a prototype showing that coronagraph can be built. It's not. It is internal coronagraph. It's not external. It is internal. So this is a diode stop we use to actually block the sun, and it's very simple in terms of operations. So moving on, all the previous work until 2021 was using sort of the model was used such that the sun was a monopole, pretty much a spherical, no structureless point, massive point. And so we realized that the sun is not a point. It's essentially, it rotates, it has extensity, and actually there is oblateness. And when light travels around an oblate gravitating mass, there is some different optical path created. When the light goes around oblate body, the light travels, has a different phase shift. So we had to account for the fact that sun is extended, it rotates, and we now have full capture, we were able to capture fully the extensity of the sun, including all the zonal harmonics, J2, J4, J6, J8. And so this is wonderful caustics that are formed in the PSF of the extended sun. We used to deal only with monopole that is shown on the right, with the monopole caustic, which is shown on the bottom of this page. Now we deal with all of those wonderful caustics. This is quadrupole, this is J4, J6, J8. And realistically, for the sun, only J2 is most important. It's the largest, 10 to the minus 7 in unitless mass, in unitless units. Essentially, this is what we need to deal with. And so this is the asteroid caustic. And this model now fully incorporated in our image capture, convolution, and deconvolution. And we are able to identify a lot of interesting features. So this is how Einstein crosses are formed. Because if the lens is not spherically symmetric, if it's oblate, the image that is being formed is not Einstein ring, essentially it's Einstein cross. And here on the left, you see the point spread function, and the cross here is the position of our telescope within the PSF, essentially. And so as telescope moves, it looks back at the sun and it sees 4 cusps that are forming the images. And those images are now, it's like, this is the Einstein crosses that we actually were able to see multiple observations of gravitational lenses. But we use this information to actually recover the structure of the source. And so that is now fully captured in our data analysis techniques. And what we have now, again, this is sort of the intensity of those, of the cusps that the telescope is observing. And that information is very useful for us to deconvolve the blur of the solar gravitational lens and actually improve the image quality. So moving on, this is what we can do today. So essentially, again, on the left, you see the image of our own planet with different resolution, 128 by 128 pixels, and again, 100,000 by 1,000 pixels, convolving it with the PSF and deconvolving it. So, of course, the higher the desirable resolution, the longer is the integration time. Because, for example, to build an image like the one we see on the bottom right, so this is high resolution image, we need to take, to build an image like that would require about 7 to 11 months of integration of collecting data. But outcome will be the image of distant object with this beautiful resolution. And so moving on, we understand that nothing is fixed in the universe. Everything is moving. Even look, the host, the exoplanet orbiting its own host star. There is orbital motion. Host star has a proper motion with respect to our own sun, and even our own sun is not fixed with in space. It actually moves with respect to solar system barycenter. And so this is on this chart, you see how an observer at 10 parsec would see our optical center of our sun moving, and within the different periods. And realistically, to design a mission, we need to be able to understand this motion and how the image will be moving in the image plane. Once we reach those distances, 650 AU, we need to understand where the image of the host star will be and where the image of exoplanet will be. And so we need to be able to chase those images, understanding the velocity and acceleration that is required on board to chase those images. And so this is what we've done. And so we have done simulations. We simulated all of those effects that are affecting the motion of the image, proper motion, planetary orbital motion, host star, and the sun motion in the solar system barycentric frame. And here you see on the left is a displacement of our sort of the modeled planetary system. So this is the, we took as a star, we took our own sun and positioned it at 10 parsec. And then we modified the orbital elements of the sort of the model planetary system quite drastically. So it doesn't resemble our own solar system, but actually it's, so we see how the stellar wobble is prominent. We need to follow this blue curve year after year. So that's in 2 dimensions. And in 3 dimensions, the curve that we need to follow shown here in blue. We begin with the 650 astronomical units, and then as we move on, the image gets slightly larger, and so we need to follow those images. And so those displacements are quite large, but then the velocities and accelerations are not. And so let me show, this is how exoplanet will look like in the image plane. The displacement, it's on a scale of what is about 100,000 kilometers. So we need to be able to chase that object on pretty much all the time, because the exoplanet is always on the go. So it's not fixed. We need to be able to have a spacecraft that is moving with the image. And then within that image, it needs to move from pixel to collect data. So this is this is 3-dimensional picture. As we start moving at 650 AU, so as we progress, let's say this is shown 20 years of mission. So essentially, we need to follow that spiral and to be able to be on the image all the time. So what are the velocities required? Velocities that are needed to chase those images on the scale of 20 meters per second for the exoplanet, exo-Earth, and roughly 10 millimeters per second for the host star. But the velocities is not the critical component. Acceleration, this is what we're after, because we need to equip our spacecraft with propulsion capabilities. And it looks like for the exo-Earth, one of the most sort of the least, it's worst case scenario shows that we have, we need to have onboard capabilities at the level of 5 micron per second squared to chase the image of the exoplanet. So the capabilities of the micron per second squared are already available in the industry, and those thrusters are available. So we don't require any magic thrusting capabilities on board. So essentially, the largest number, the largest acceleration that we need to achieve on the spacecraft, it's on a scale of a few microns per second squared. The challenge, of course, is that this thruster needs to work for the entire mission duration, because it needs to follow the image. But with understanding how technology is evolving, we don't think this is a showstopper. So in fact, there are quite a few small companies already develop those capabilities. And by the time the mission will be will begin development, this will be fully at hand. Moving on, our mission already includes the discussion of the planetary motion, image motion in the mission design, and we have developed all the appropriate concept of operations to capture the images.
Slava,
yes.
Another question for you is to what extent do you need to know, have knowledge of the relative motion to the sun of the target object, in the distance, or is that something you can discover in the course of your observations and then refine your observation strategy on the basis of the new information? In other words, how much does this have to be figured out in advance, and how much can be figured out on the fly, if you will, by your telescope?
Mark, wonderful question. Initially, I thought that we have to have all the information before we put our vehicle on a launch pad. And the reality is that we should not. We are not. We can really monitor the movement. First of all, as we launch, the host star will be always visible. As we reach the optical, the imaging region, the strong interference region where the imaging will begin. So the light from the host star will be greatly magnified as well. If we position a spacecraft at that location where the light from the host star is greatly amplified, and we trace that amplified light from the host star to determine all the orbital details of exoplanet movement, and if any proper motion, any other elements of orbital dynamics. This is all easy to determine. Just here on this chart, let me show how we do that. So essentially, imagine once we reach the strong interference region where the light from the host star is amplified, and we're talking about the light will be from the host star will be comparable to the brightness of the solar corona, so it's quite bright. And as we approach the optical axis of the host star, if we are still not on the optical axis, we see two bright spots on the sensor. See here on the bottom right chart, you see the Einstein ring is not fully formed, but we will see two bright spots. As you move closer to the optical axis, those two bright spots are developing into arcs that are not yet closed, but they're getting larger. As you move further, much closer to the optical axis, those arcs are now touching each other, and so the Einstein ring is formed with uneven brightness. And when we're exactly on the optical axis, so we will see the full bright uniform Einstein ring in this case. So what I'm saying is that this information provides us with very sensitive guidance signal. We can fly two small spacecraft that will not be on the optical axis. And so they will be observing the host star light and will monitor where the optical axis of the host star all the time will be present. By actually see these two bright spots on the bottom of this chart, they're very sensitive to direction towards the optical axis. And then the brightness, the relative brightness of these two spots on the sensor will provide you essentially the distance towards the optical axis. This is the unique information that actually will help us not only to identify all the dynamics that this particular target system is involved, including proper motion, including orbital dynamics, and any reflex motion, but also it will guide us to determine orbital parameters of the exoplanets. For example, if there will be several exoplanets, we will know orbital parameters of each of those exoplanets by basically monitoring the light of the host star. So before we launch, we need to know high-value targets, so to speak. There should be indication that this particular target is of high interest, right? And so I assume that will be done with upcoming missions. Let's say maybe WFIRST will develop a good understanding for the target list. And so we'll have a good knowledge that there may be some atmosphere available on that exoplanet. Then we launch a spacecraft. But orbital dynamics is not a key. We need to understand, that will be determined during the mission time. Because to get there, it takes about 20 years to get to this distance. And so during the transit time, we will be able to determine all the critical elements of the orbital dynamics. Did I answer your question?
Yes, yes. No, that's good, very helpful. Thank you.
Good. Moving on. So essentially, how do we get there? The challenge, of course, I was throwing the numbers, which are the 547 astronomical units, 650 astronomical units. It's easy to say, but very hard to reach. And you would like to reach those distances within reasonable time, not centuries, but in decades. And so this is our primary challenge. The challenge is how to get there, to those regions. We need to move fast. So there are two ways to think about this. It's either move fast or live longer. And I suggest we do both, right? I suggest we do both. And so realistically, getting there it requires speeds of 20 astronomical units per year. So as you know, the fastest spacecraft that we flew is Voyager 1 and New Horizons. Both of them achieved velocities of roughly 3 astronomical units per year. So we need to increase this number by a factor of 7. How do we do that? We looked at a number of opportunities: chemical propulsion, solar thermal, nuclear electric sail. So the very interesting capabilities, they're being developed. And of course, chemical propulsion is the most reliable. And so, but there are some challenges for those missions that utilize this propulsion for achieve very high transit velocities. We need to get very close to the sun. A very heavy thermal shielding is required. And realistically, this is why the velocities, the largest velocities we can get with chemical propulsion today is roughly on a scale of 15 AU per year, which is good, but not enough. And so we decided, after scanning this landscape, we decided that as a scouting mission, I think we need to rely on the emerging technologies such as small spacecraft, because the access to space is now reduced drastically, the cost to access reduced drastically, technology is being developed. And so essentially we can use now solar sailing as the primary capability to reach those distances in the reasonable time frame. So solar sailing is a technology that is now being also developed within NASA and international partners. So you see that interplanetary small, there are several key technologies that are used for this mission. First of all, the interplanetary small sats. Of course, we all know about the Marco 1, Marco 2, the small 6U machines that were used with the inside lander. And so these were magnificent first demonstrations of communicating with the small sat on interplanetary scales, delivering good science when InSight was landing on Mars. But now small mass, it's actually very good, because now we can think about solar sailing. The materials for solar sails and the materials to sustain thermal load in the solar proximity are being developed, and some of them are already at hand. We are talking about missions that, let's say, 0.25 astronomical units going to the sun at that distance. And so those materials are already available. We can benefit from their availability. Rideshare is another important capability, because now we can fly our small sats as a rideshare, reducing access to space, and therefore the total mission cost will be much smaller. So solar sail is, as I mentioned, there were several demonstrations like Icarus, JAXA, Japanese space agency. Icarus flew to Venus on solar sailing capability. And as we speak, so a light sail spacecraft launched by Planetary Society is going through the second year of operations in space, performing beautifully. So there are many other missions. For example, NIAC Scout will be launched soon. Then there will be several other missions that are being developed within NASA and international community. So solar sailing is being developed quite rapidly. But as you see on those charts, the sails that are being used in the community are planar sails. The planar sails not very stable for the attitude control. So therefore, we actually designed a very different sail structure. Okay, so how solar sailing works? We have, it's like a sailboat. Sailboat benefits from having, sail and the wind and the rudder. So essentially, when wind blows, the sail actually captures the pressure from the wind, and the rudder allows you to control the course of the sailcraft. Of the sailboat. And with the sailboat, you can go almost against the wind, not directly, but almost against the wind. With the sailcraft, we are using the same approach, and we developed a very similar approach where the sailcraft acts as a sailboat. So in this case, the solar wind is not solar wind, the solar radiation pressure. We use it for like a wind on a sailboat, but then sailcraft has the sail. Instead of rudder, we have reaction wheels. So all the capabilities that we have now developed for sailboats are now fully applicable here. We can actually use our sailcraft go against the wind, following almost towards the sun. And so, but the solar momentum, when the solar photons are sort of impacting the sail, they're transferring momentum, and the sailcraft actually works because of this. So this is our design. On the left, you see the primary sort of the design that came that was developed in 2010 by Sunvane. So it's a Sunvane design developed by Lagarde Corporation here in Los Angeles area. But now Explore, our industrial partner, took it a little bit further and developed the vaned approach. On the right, you see a vaned approach shown here. You have a truss, you have 6 vanes that are articulatable, and they can be used as a sail, as a sort of tilt those vanes, and so the whole vehicle will resemble a sailcraft. With this type of approach, we can go from high Earth orbit. We can pass by Mercury within 6 months, and then we'll be diving towards the sun. And within a month after that, we are moving with very high velocity. So that's the whole idea. So with those veins, with the solar veins, those solar veins can have the photovoltaics embedded on them. Solar veins can have radio antennas embedded on them, so potentially larger aperture for communication purposes and for power when we go near the sun. And so to demonstrate those capabilities, we actually developing now something called technology demonstration mission. And this is the flight chart that we would like to have for our technology demonstration mission. We are using rideshare capabilities, launching from Earth, going all the way to high Earth orbit, and where we assemble our spacecraft with direct injection, or pretty much with C3 equals 0. We start falling towards the sun. During the initial flight, during the ingress, we verify multiple technologies, communication, attitude control. We have increased power, lots of interesting features on the sailcraft. As we reach perihelion, we are working now with autonomous systems, checking environment, and then as we start egressing, we are moving quite rapidly. So that's the logic of the operations. We can talk about this a little bit later, but this is the idea how we can benefit from solar sailing. And okay, so the next chart. Okay, so this is just a high-level overview of mission towards the solar gravitational lens, and I decided to keep it deliberately at the high level because there's so many details. As I said, we launch with rideshare, we go to high Earth orbit, then we assemble. There will be not one spacecraft, but several small spacecraft, because going to small sats, the costs are significantly reduced. We are not talking about a sort of flagship mission here. We're talking about a fleet of small vehicles that actually work cooperatively, and they have small telescopes on board that will be able to track the Einstein ring once the telescope reaches the strong interference region. So once we get to the high Earth orbit, and so we start diving towards the sun, and then going after perihelion, we're moving with high velocity. After about 20 years of transit, there are plenty of secondary science. I can talk about this, a lot of interesting things, but this mission design was actually, it was developed to achieve primary science objective, imaging of the exoplanet. Therefore, I'm focusing only on the imaging. Once we get to the focal region of the solar gravitational lens, we have several spacecraft dedicated to track the amplified light of the host star, which is establishing local reference frame. And then the other group of small sats will be now following the image of the exoplanet, moving pixel by moving with its motion in the image plane and imaging it pixel by pixel. So that's the logic of the mission design. And okay, I guess I want to move. Okay, moving on. So this is our technology demonstration mission that we are building now, and in the year we should have a PDR demonstrating the capabilities of this vehicle. Look at the numbers. Total mass of that vehicle is 5.4 kilograms. And so this vehicle may host a payload at this moment, 1 kilogram payload. And so this vehicle will demonstrate the speed of roughly 6 to 8 astronomical units per year. Think about using a vehicle like that, study solar system. So this is our technology demonstration mission, but we offer this mission for you to think about accessing deep regions of the solar system and sort of within our lifetimes, much faster, more capable spacecraft, like a scouting of the solar system with vehicles like this. The cost of this vehicle is under $20 million. So that's basically, it's a completely different cost paradigm, a very different situation where we can think about missions to KBOs, missions to deep solar system objects, and actually also chasing those interesting interstellar visitors that we actually start seeing quite regularly now. So this is our TDM concept. Moving on, this is the status of the development of the TDM. We have a prototype. You see those veins sitting in the assembly. So those veins, it's 1/3 of the prototype size, and this is the prototype being assembled. It's it's a hanging demonstration. So now it's fully capable here, but it's 1/3 of the total size of the future vehicle. It's to demonstrate the assembly processes, is to demonstrate the capabilities. And actually, what is also interesting is that thermal design, we did the thermal analysis of this vehicle, and what we show that we already are capable to satisfy any thermal thermal environment at the 0.25 astronomical units distance. So essentially, all the materials that we use for the vehicle and the solar saline materials are already passing the threshold. The only couple elements that are still here, star trackers and the reaction walls, shown in red. So these are the temperatures that those instruments will observe. So we need to work a little bit on those, but pretty much it's not a big problem. So realistically, in the next month or two, we will come up with a design that will make the whole sort of payload to be green, meaning that the thermal environment near the sun will be fully addressed by the design, and so we can actually start thinking about flying those missions in the near future. So that's the design, and that's the technology demonstration mission. That's where we are now. So as I mentioned, the solar gravitational lensing seem to be the only means for us to directly see, confirm, and study exolife. This is where we need your help. We now understand optical properties of that lens, and we have a very capable mission design. Now we have the instrument. Let's work together, study how we can actually use it to observe exolife, or detect biosignatures on those objects. Because think about spatially resolved spectroscopy. Essentially, we can identify if that particular emission line is originated in a particular area on the exoplanet. Questions like that were not possible previously. With the solar gravitational lensing, we seem to be at the very new reality where we need to ask those questions and start putting them in the mission design, so that the mission, when it flies, will be able to actually discover and to study those very exciting signs of life on the alien planets. So the plan here is a new term plans and the technology strategy, transition strategy. Our phase 3 will be over in a year. We are now developing something called public-private partnership, where we will continue with technology demonstration missions, with improving the technology and moving the mission concept towards actually funding by the community and space agencies. So in the 2022, the next year we'll form the public-private partnership, and we'll start flying those sailcraft to demonstrate the maturity and the technology reaching ultimately the higher velocities. So think about putting instruments on those TDM flights that will deliver data from the distances beyond 5 astronomical units within a year, going there, maybe even faster. So we are breaking the paradigm that planetary sciences community was kind of within for the last 30, 60 years. Now we are aiming at the fact that new technology will allow us to access the sort of deep regions of the solar system much faster. And then within the next decade, within this decade, we are planning to have sun accelerated flights, achieving velocities of 10 astronomical units and beyond. And then we hope that the project will begin, project itself will begin by in the next decade. All seem to be that all our analysis suggests that although there are plenty of challenges, and so the mission is not simple, but we have not found those showstoppers that will preclude us developing this mission. We just need to put our heads together and come up with the most affordable and most exciting mission design. Thinking about the planetary sciences community, I mentioned briefly that this type of technology is actually essentially there is a new paradigm: fast, low cost, nanosatellite craft use in the studying solar system. Think about this is the solar system. The first light craft demonstration flight will achieve velocities of 5 to 6 astronomical units per year. Then we can actually chase one of those interstellar objects with the spacecraft, with the sailcraft, which will require 7 to 9 astronomical units per year. Then KBOs, those missions that will fly in the next few years, in the next 5 to 6 years, we should be able to reach velocities of 10 to 14 AU per year. This is where we can start exploring distant regions of the solar system. And of course, the SGL proper will come in the next decade. But this is what this new technology enables us. And what we think, when we think about the solar gravity lens, it is something that will help us to build the community that will rely not only sort of science, but also on technology, because the technology that this mission is requiring, this is quite exciting. We need to have autonomy on board. It has to be autonomous computation. It has to be communication power. All of the mission design elements will be pushed beyond the limit and to the limit. And so essentially developing new technologies to address the objectives of the solar gravitational lens will advance the entire set of technologies that we are now using for accessing solar system and flying missions, exploring planets in the solar system. So this is quite exciting. And I want to leave you with just one slide. So this is the slide. This is our own planet seen in physical colors. As you know, our eye looks at objects and a little bit biased towards the green color. So this is the image of our own planet in physical colors. And my hope is that, I guess by the time I'm 100 years old, I should be able to see this object come to existence. And so we will be able to see the image of exoplanet in our neighborhood, in our stellar neighborhood. And this is something that actually quite exciting. And we will be able to see for the first time objects that are within our stellar neighborhood, potentially with life detected on their surfaces. So think about this, and let's talk more about the opportunity. Thank you very much. I guess at this moment, I'd like to stop and open for questions if you have any.
Thank you very much, Slava. Fascinating stuff. People, if you want to ask questions, then just unmute and speak out. It's not so crowded that I think we can't do that. But I'll ask the first question, Slava. You know, let's say we were looking at something that's just like Earth, you know, just like Earth is today. Would there be enough signal noise in an image to detect light pollution on the night side of the planet?
I love this question because with the technology we can see if this civilization, if they have using the same carbon fuel, so carbon fossil fuel, right? So do they have the pollution on their own atmosphere? But yes, you're right. I think we will be able to. We have a very significant signal to noise ratio. We get signal to noise ratio of roughly 7 in about 2 minutes of integration time. So we're talking about realistic numbers here. So the SNR is, and I'm talking about 1 meter telescope. The larger telescope we fly, SNR will be even higher. So we have a very good sensitivity there. So just for you, for the most complex objects, for the distant and maybe having significant brightness on the background, we are seeing the numbers of about 60,000 photons a second compared to roughly 70,000 photons a second from the solar corona. So that signal noise ratio is quite significant there.
Mm-hmm, mm-hmm. Wow.
And
yeah, I was wondering about the number of photons per second because being an old telescope jockey, that you imagine the size of the our solar corona seen from 100 AU away, and it's like, gee, how many photons is actually going through that?
A lot, and so yes, we have computed all of that. So we know the not only the noises coming from the solar corona. Essentially, there is some leakage from the coronagraph because we don't block entire sun. There will be some leakage, right? And so we actually now account for the leakage from the sun, and also there will be some background noise as we observe those objects. There will be some objects on the background. So we need to be able to resolve our signal on the reasonably noisy background. And so for now we see that seeing those 10,000, maybe 60,000 photons a second, it's a quite comfortable number.
I have a question in chat here from Nancy Kang. Could you do a 3D image of the planet?
Yes, we can. Yes, we can. And so that would imply flying another. That would imply flying another instrument that will be probably coherently linked. So it's a coherent observation from different, from different spacecraft. But yes, we thought about this, making 3D images. And essentially, that will allow us to remove cloud cover much faster compared to just single or maybe a cluster of telescopes that are not interferometrically linked. It will provide a little bit more complication to the instrumental suite, but yes, it's possible. So we can do a three-dimensional orbital, sort of the image reconstruction. And also, we each time we look at the exoplanet, we're seeing only phases of this object. We don't see the full phase because, right, so it's orbital dynamics. So essentially, we need to look at those phases and collect information to be able to recover surface features on that exoplanet. So we do account for this interesting dynamics of the system which we observe.
Yeah.
Yeah, I have a question. Did I understand it correctly that it will take you like 20 years to build up the Einstein rings?
No, it's to get to the strong interference region. It's to get to the distance of roughly 650 AU. Once we get there, Einstein ring is there. It's waiting for us because basically, light that travels by the sun is being affected by solar gravity. Einstein ring is there. So we need to go there. And so this is what 20 years it takes to get to that point. But once we're there, the signal to noise ratio for single pixel, it's anywhere between 2 minutes to maybe 15 minutes per pixel. And that actually translates into the mission design and mission longevity. And I'm talking about 1 meter telescope. If you fly 2 meters or maybe 3 meter telescope, that actually cuts significantly into the shortening the mission. We'll fly maybe several of those small sats. That will actually increase increase the capabilities of our mission. So yes, there are many ways to reduce the image collecting time, but to get there, this is the primary challenge, is to get there in reasonable time.
So how many exoplanets could you image in, let's say, a month?
It is wonderful. So the reason, once we are using solar sailing, we can look at only one planetary system. So that means if we observe, our sun from a distance, we will see all the planets. But that will be only one single planetary system. With the solar sailing capability, we are not thinking about refocusing, repointing our instrument to a different planetary system because there is not enough propulsion capability. When the technology that Mark mentioned in the beginning will be available, then I guess it will be at will to move lateral motion, actually study other exoplanetary systems. But at this moment, it's a single planetary system. But then also, if we have one or two or several high value targets to explore, because of the mission cost, it's rather affordable. We're not talking about many billions of dollars. It's not a very significant cost. We can fly several of those missions and to study those planetary systems at maybe the same time.
Thank you.
Any other questions? Okay, Slava, thank you very much. This has been absolutely fascinating. Really love to hear about this mission, and we'll enjoy hearing more about it as time goes on.
Excellent. Thank you very much for the opportunity, and reach out to me if you have ideas or questions how this mission can be even more relevant for planetary physics and for other potential applications. Thank you very much.
And it really underscores that exoplanets really belong in planetary science.
Absolutely. Absolutely. This is the key point. Exoplanets should be studied by the planetary community because planetary community has the tool and understanding and appreciation what needs to be studied, what needs to be looked at. And so this is where exoplanets should belong to. So,
this technology would really put exoplanetary work into the larger rubric of comparative planetology.
Absolutely. Excellent. Thank you very much. And
thank you. And thank you everybody for calling in.